All right, so in this video, I would like to give you a simple numerical example of a transmission line terminated with a load. And I think by looking at this example, you'll be able to learn a lot of how the voltage and the current behaves on a transmission line. So let's see what we have. We have a ZL here. This is given as 50 plus J 57.7 ohms. And we have a transmission line with a characteristic impedance of 50 ohms connected to the load. The load, as usual, is placed at L is equal to 0. And then what we would like to understand is basically how does the voltage and the current look like as I'm moving away from the load. So we would like, in other words, to calculate the magnitude of the voltage and the magnitude of the current as a function of L. I have actually given you some additional information here just to make the calculation simple. So for example, the magnitude of the incident voltage wave V0 plus is given as 1 volt. So as usual, you can start by looking at the reflection coefficient at the load. So you would have that gamma L right here is equal to ZL minus Z0 over ZL plus Z0. And if you plug in the numerical values, you will find that gamma L to be equal to 0.5 with an angle of 60 degrees. So you can go ahead now and use the expressions that we learned before in terms of the magnitude of the voltage and the magnitude of the current. So here's the magnitude of the voltage. So it's going to be equal to 1 plus 0.5 e to the j 60 degrees minus 2 beta L. And if you also apply the same thing for the current, you will get the expression right here. Again, you should really recall that the voltage at any point in time, so for example, at any point along the transmission line, for example, at this point or this point or this point, is always a function of time. So of course, at any of those 3 points, it will oscillate as a function of time, and it will be a sinusoidal signal. However, the magnitude at each one of these points will be different. So if you would like to know the magnitude of the voltage at each and every single point here, then you have to use the expression I'm giving you right here. And similarly, if you would like to learn the magnitude of the current that flows at every single point along the transmission line, you have to use the expression right here. Now, you can study this expression and you can get some interesting information. For example, as you can see, there is this term here of 60 degrees minus 2 beta L, which actually will imply a periodicity along the transmission line of 2 beta L. So every 2 beta L, or every 360 degrees, things basically will start repeating along the transmission line. You can also guess here what will be the maximum voltage magnitude and the minimum voltage magnitude. For example, the maximum voltage magnitude will be equal to 1.5, while the minimum voltage magnitude will be equal to 0.5. Now, all of this will become a lot clearer if we go ahead and graph these equations into a nice graph. So this is what I have done in this slide. This is here the magnitude of the voltage. So what you will see here is the magnitude of V of L. And of course, L is equal to 0 right here is where my load exists. And if you take exactly the expression I gave you before and you plug it into your favorite software, you will actually get a graph like this. Now, we said before that there is a periodicity of 2 beta L. And you can actually see here that every so often results do repeat. So for example, if you ask the question, what is the distance between two successive maxima? For example, the distance between this and this minimum, of course maximum and minimum is the distance will be the same. Of course, in that case, you will find out that the result is lambda by 2. So every lambda by 2, you will actually find a minimum of the voltage along the transmission line, or of course, every lambda by 2, you will find a maximum of the voltage along the transmission line. Now, the distance between a maximum and a minimum, so the distance between this maximum here and this minimum here, is actually a quarter of a wavelength. So every quarter of a wavelength, things change dramatically. And here I gave you that the wavelength is actually 3 centimeters. So if you were to actually fabricate this on, let's say, a PC board, you would find out that you move the PC board just 3 centimeters, barely a little bit over an inch, and you will find out that you went for a voltage maximum to a voltage minimum. Now imagine if you were doing this thing at a higher frequency and the wavelength was maybe only 3 millimeters, or perhaps even 300 micrometers, then you will realize that just a tiny bit of difference along the length of the line will make a big difference on the voltage or, of course, the current. You can also see some other things here. So, for example, you can see that at the location of the load right here, you actually don't have a voltage maximum or a voltage minimum. And in fact, it turns out that in order to get a voltage maximum or a voltage minimum, if you go back to the equations I showed you, you'll find out that 2 beta L has to be equal to 60 degrees. And indeed, once you move far away enough and you hit that, you will actually find out that you will hit a voltage maximum. And of course, if you now move, eventually you'll hit a voltage minimum and another voltage maximum and so on, just as we discussed. Now, from this graph, you can also see that the maximum voltage, as we predicted before, is going to be equal to 1.5 volts. This is the maximum voltage magnitude. And the minimum voltage magnitude is going to be equal to 0.5 volt. So again, one of the reasons I really love this graph, and I really encourage you to study this quite a bit, and in fact to go ahead and plot it yourselves, is because it does teach you a lot in terms of what's happening in the transmission line. And of course, you can do exactly the same thing for the current, and you will basically get the same information. So I hope this has been helpful. Talk to you next time.